Welcome to my talk about the fine-scale complex fault structure and the kinematics along the Central San Andreas Fault. This figure shows the map view and the cross-section view of earthquakes and magnitude larger than 4 focal mechanisms along 180 km long Central San Andreas Fault. Although this is a highly localized fault zone, with major earthquakes located along the fault, and their focal mechanisms are consistent with main shock slip. It exhibits diverse seismic and aseismic deformations, with full spectrum of fault coupling from fully locked to fully creeping, and abundant small earthquakes showing complex fault geometry and slip motions. Moreover, there's no record of a large historic earthquake, but with repeated magnitude 7 to 8 earthquakes to the north and south of this fault segment. It leads us to question about what controls the variations of seismic and aseismic deformation along the Central San Andreas Fault, and what is the potential of future large earthquakes occurring on this fault. To understand this question, we use the seismicity and focal mechanisms of magnitude larger than 4 earthquakes, which colored in blue, repeating earthquakes, colored in red, and magnitude larger than 1 earthquake, colored in black. The right side shows the rotated map view, cross-section view, and the temporal variations of the used datasets. We first use repeating earthquake and magnitude larger than 1 earthquakes to constrain the main fault orientation using principal component analysis, and find that the fault is overall vertical with a strike orientation from 120 degrees on the northwest to 140 degrees on the southeast of the fault. We further calculate the horizontal distance from these earthquakes to the main fault, and the azimuthal difference from the strike of the focal mechanism to the strike of the main fault. And here are the cumulative density functions. We find that almost 100% of magnitude 4 earthquakes and repeating earthquakes are located within 1 kilometer from the main fault, and over 90% of them have azimuthal difference within 20 degrees from the main fault. But for magnitude larger than 1 earthquake, there's about 80% of them located in 1 kilometer and have azimuthal difference within 20 kilometers from the main fault. Based on this observation, we made the assumption that most magnitude larger than 4 earthquakes and repeating earthquakes occurred on the main fault, while magnitude larger than 1 earthquakes both occur on the fault and off the fault. To understand the deformation on the fault, we propose a mechanical model of a freely sleeping shallow seismogenic layer with several locked patches and a 34 mm per year interseismic deep sleep rate beneath the seismogenic layer. The locked patch is set based on the location of magnitude larger than 4 and magnitude larger than 1 earthquakes. Then we use the Poly 3D to simulate the creep rate on the fault and the sleep direction on the fault. Here we compare the modeled creep rate with the observed creep rate estimated from the occurrence rate of repeating earthquakes. Then we also compare the modeled sleep direction with the observed sleep direction estimated from the rake angle of repeating earthquake focal mechanisms. Last but not least, we also compare the along fault deformation estimated from the model, which is shown in red, with the observed surface deformation from the INSAR data. The results show that the modeling results are highly consistent with multiple observations. We further look at how the modeled fault normal displacement is related to the on-fault and off-fault earthquake properties. Here shows the modeled fault normal displacement, and we calculate the average for normal displacement for the top 9 km depths, which is shown in black curve. Then we also calculate the spatial variation of focal mechanism properties estimated from magnitude larger than 1 earthquakes within 3 km epicentral distance from the fault. Here are several values focal mechanism properties we're trying to compare. The green curve shows the azimuthal difference between the p-axis of the composite focal mechanisms and the main fault orientation. The red color shows the percentage of the oblique reverse faulting events, and the blue curve shows the focal mechanism heterogeneity. We found that with increasing fault normal displacement, there's an increase of the angle between the p-axis azimuth to the main fault strike, and decreasing percentage of oblique reverse faulting events, and decreasing focal mechanism heterogeneity. Here is a possible mechanism of how the fault normal displacement affects the surrounding seismic deformation. When the fault normal displacement is smaller than 0, it will generate fine-scale restraining band and cause more oblique reverse faulting events and lead to the counterclockwise rotation of p-axis. When the fault normal displacement is larger than 0, it will generate a fine-scale releasing band and cause more oblique normal faulting events as well as the clockwise rotation of p-axis. So the modeled fault displacement can cause a fine-scale fault twist and significantly affect the earthquake focal mechanisms around it. Here are the summaries of this work. To sum up, the variation of the fault strength along the fault can strongly affect the seismic and aseismic deformation both on and off the fault. And this analysis can be further applied to other localized fault zones for better understanding of fault mechanics and the potential of major earthquakes. If you have any questions and suggestions, feel free to contact us at the Berkeley Seismolab. And thanks for your listening.